So it's a great pleasure to be here, and I'd like to thank the organizers for inviting me. This talk will sort of be a summary of what I've been up to for the last couple of years. And pictures are something that I wasn't always used to thinking in terms of, but they really permeate mathematics. There's nothing new about pictures. And I found this book in the Clare College Library, which was one of the first printed editions of Euclid constructing an equilateral triangle with two circles. So pictures, we heard a lot in Vaughan's talk, and they come into practically every part of mathematics. But I've been having a lot of fun with pictures with Zhengwei, who was Vaughan's student, and started to get together with him just a little less than 2 years ago. So we started by talking about mathematics and physics, and then eventually quantum information reared its head when a student, Alex Wozniakowski, remarked what we were talking about seemed related to quantum information. And then we got interested in various languages to study these problems, and we came back to mathematics and physics, and where it's leading I'm not sure, but all I know is we're having a great deal of fun. And I'll describe some ideas. I don't think there are any theorems in my talk, so it's, in spite of that, is a mathematics talk, but we'll see how it goes. So the picture journey started, let me give a bit of the overview. When Zhengwei came and we wanted to he wanted to teach me planar algebras, and I was telling him about parafermions, which I was thinking about at the time, and we put them together with planar para algebra. And then we found that Papa, mainly parafermion planar para algebra, has a very nice reflection positivity property, which is connected to the positivity property in Hilbert space that Vaughan mentioned in his talk. And then we got into this quantum information with two strings coming from planar algebras and natural way to describe certain transformations, and four strings were in the background. And we started to study the pictorial Fourier transform, or string Fourier transform, and we wrote some, we thought, interesting papers, one of which still hasn't been published, but will be soon. And they connect to quantum information, and I'm going to talk very much today about the quantum information side of this work. And the quon language came out of that, which is the language we're interested in now. And you'll hear a lot of that from Zhengwei in his talk tomorrow. This very nice photo taken in my office a few months ago. And it connects now with a bunch of mathematics, which I'm not going to really get to today. So Freeman Dyson wrote this article, Birds and Frogs, in which he described two types of mathematicians. One who flies from place to place and gets the global view and touches many interesting ideas, and frogs who gravel in the dirt and prove theorems but get into lots of interesting detail. And Dyson describes himself as a frog, but says you need both type of mathematicians. And I guess I'm more of a frog, and Zhengwei is a bird, and so I really am going to enjoy the picture, that overview that he'll give tomorrow. So what I'd like to start out by talking about in specific detail is the parafermion algebra, n parafermions of order d. So that means you have a number of unitary transformations C, which are indexed by label 1 through n. And you take a dth root of unity, which is the fixed number d. So all the things I'll talk about today are finite dimensional. Hope that they'll come to infinite dimension, to meet infinite dimensional problems, the type that Vaughan was talking about in statistical mechanics and quantum field theory. But the background here I'm talking about is all finite dimensional. So these parafermions satisfy the dth power of the unitary is 1, and they have this commutation relation that Ci Cj is phase times Cj Ci for I less than j. Now, in this algebra, often the square root of this parameter q comes up, and we call it zeta. And it's good to have zeta to the k squared well defined in the group ZD, so we take zeta to the d squared to be 1. For even d, it doesn't matter. For odd d, you have to choose the right square root. So I had been interested in parafermions and wrote a couple of papers with Fabio and Voss, but things turned in a completely different direction when Zhengwei came to Harvard, and that and I should mention that the case d equals 2 is the usual fermions, and these satisfy Clifford algebra. So in quantum information, as I mentioned, we'll connect to, there are some other unitary Pauli matrices that come up everywhere, and they're called X, Y, Z. They're generalizations of the spin matrices sigma X, sigma Y, sigma Z. And they also have dth power equals 1 and satisfy this same type of relation, x times y equals q, y times x. But in addition, x, y, z is a constant. It's the square root of q. And those cyclic permutations. So these are not new. And in the case d equals 3, that goes back to this paper in 1883, where Sylvester called them nonions and solonions. And this is, it's funny that mathematicians sometimes used to publish in the Johns Hopkins University catalog. And this is from the University catalog of Johns Hopkins. So here you have the relation Mn equals rho Nm, and down here the relation xyz equals zeta is the relation Mn cubed equals 1. So if we come back to the Pauli matrices, there's a 2 parafermion model of xyz, and that's well known. It's, you take x equals to the second parafermion, y equals the inverse of the first, and z equals zeta times c1, c2 inverse. And they satisfy the algebra I claimed, and this is a calculation if you want to do it. Okay, so we started by relating these pictures to planar algebra pictures, and to denote the parafermion as a charged line in a planar algebra. So for the parafermion operator C, we just denote it by a 1 and think of that as 1 power of the parafermion. And if you have k of them, c to the power k, you write a k there. And so for the parafermions, they multiply in the normal way. C to the k times C to the L is C to the k plus L. And we take the charge to be in the group ZD, so D is congruent to 0, and 0 we just don't write a label. And if you want to denote a string, the string corresponds to the index I, and so here I've written the I underneath. And so this Ci to the k, Cj to the L is a k here and L above it, which is the convention in planar algebras of multiplication vertically upward. So the parafermion relation as a picture is that if there's nothing in between the ith and j string, C I to the k, C j to the L is q to the k L times the product in the other order. And we call this a para-isotopy of the diagram. That is, instead of the diagrams being invariant under isotopy, they have this phase, and in the non-abelian case this would be more complicated, but here it's abelian, and that corresponds to parafermions. And coming back to the Pauli matrices, then the diagram for the Pauli X is 1 on the second line. There are 2 lines corresponding to C1 and C2. And the -1 for the Pauli Y. And the Pauli Z is a little more sophisticated. Now, this para-isotopy is related to what we call the twisted product. And if we take the parafermion relation, where Ci to the k, Cj to the L, when reversed, has this diagram. The picture for the interpolation, when the k and L are at the same vertical level, is given by the square root of q. So we call this product with k and L on the same level the twisted product. And in fact, this twisted product we used in the study, I used it in the study with Bass of reflection positivity, which come back to, but it very naturally comes up in the framework of pictures here, and means that you introduce this factor zeta to the minus KL. And these twisted products, which are neutral, multiply in a very natural way. They just, the charges just add. So the Pauli Z matrix is just 1 minus 1 in this notation, and this twisted product absorbs the square root of q. So this is equal to zeta C1, C2 inverse. So here are the 3 Pauli matrices. There are 2 of them with unit charge and 1 neutral. So in planar algebra, it's important to introduce trace on the diagram and the quantum dimension. And so the trace of this line is just got by closing the line into a circle, and it's normalized by the dimension delta, and the trace of any charge is 0. So the normalized trace, if you have transformation with m lines, is given with 1 over delta to the m. And therefore, you can have this pairing, which Vaughan mentioned in his talk, A with B as the adjoint, which is the planar algebra adjoint, the vertical reflection of the diagram, and taking its trace. And the famous theorem of Vaughan is that delta is, for positivity, must be in the range to infinity or have the values 2 cosine pi over k. And in the case where these charges are around, that is still true, essentially the same proof with normalizing delta by square root of d. So in order to have a trace that gives a Hilbert space, as Vaughan mentioned, you need this index condition. And the smallest value of delta over d is what we call papa. So then we have the basis for the GNS Hilbert space. And diagrammatically, the direct notation for the basis vector is k, and the picture is just a cap with a charge k, and the normalization factor. So if you wanted to calculate, for instance, the matrix X, Pauli matrix times k, you put a 1 here, which X is 1 on the second string, and that gives a raising operator k plus 1. And this basis is a basis for the Z transformation, because if you apply 1 minus 1 to the basis vector k, then if you move the 1 on the left up, to move it away from the same level, you get a factor 1 over zeta. To move it past the k, you get a factor q to the k. And so that's what it is. And then you would like it to be an eigenstate, so you'd like 1 on the first string to be zeta times 1 on the second string. And that's the condition for that being a z basis. And so if you iterate that, if you move charge k across a cap, you get a factor of zeta to the k squared. Okay, so the dual basis is the vertical reflection, and that's measurement in physics or quantum information. And the resolution of the identity is in the straightforward picture in this notation. And that corresponds to this algebraic picture. And the braid is just the Gaussian in zeta, modifying this multiple of the projection. And omega is a phase. It's the sum of zeta to the, it's the trace of the Gaussian matrix. And with this braid, the charge can pass under the braid, but it can't pass over the braid. So the ordinary Fourier transform is given by the matrix with elements Qij. That's the Fourier series. So if we take this neutral transformation with charge I and minus I, its Fourier transform is just sum of Qij times the neutral j. Okay. Now, this string Fourier transform is Acciano's rotation of graphs, where for a transformation with a number of lines coming out for the input and number for the output here, you permute the points cyclically by 1. So you take this input down to be an output and this output to be an input. So some examples, if you rotate this over to the right, then by cyclically permuting you move the k from this point to this point. So taking a charge over the cap is the same as introducing this Gaussian factor, because we had this identity that the charge on the left was zeta to the k squared times the charge on the right. And so this acting on vectors, this string Fourier transform conjugates x to y inverse. Now, this string Fourier transform is very complicated. It doesn't act the same way on transformations as on vectors. So if you have a transformation with 2 lines in and 2 lines out, it's neutral. It just turns it on its side. And so some examples are, if you take the identity transformation, you get a multiple of a projection. So it doesn't preserve the rank. And if you do it again, you get back to the identity transformation. And then there's a very simple argument, one line, to show you one proof that the string Fourier transform is some generalization of the Fourier transform. That if you do it on this multiple of a projection, then you get this diagram. You take this line down, and the minus k is above. You take this one up, but when you take this one down, you have k on the wrong side. So first you have to move k, minus k, over to the left, and that will remove the factor of zeta that you get by bringing the two to an equal level. So you have this end result, which is reflection symmetric from right to left, if reflection reverses charge. So if you just insert the formula for the resolution of the identity, the sum over alpha, and if you now split the k, move it, the minus k up, you get this factor zeta to the k squared. And if you now take this k, you'd like to bring it over to the right side, but first you have to bring it up past the alpha, so you get q to the k alpha. Bring it over. You have this formula here. And if you now translate alpha to alpha minus k, you come back to the Fourier transform. So this is just the same as the Fourier transform on those neutral elements. It's a well-known result, but here's one line. So on matrix units, this is more complicated, and it doesn't equal the Fourier transform. So in quantum information, one is interested in entanglement, and that is a generalization of the product states, which is a Bell state. The simplest one is if you have a product of 2 states and you take a sum of 2 products, no longer a product, and that's called an entangled state. So if we have a product of two caps without charge, or possibly n caps, as in this picture, and take the Fourier transform, then you would take the line on the left to permute cyclically and bring it over to the end. And we call this, after normalization, the state max for n qubits, where the qubit is just this individual one excitation state that I talked about before. So here we have a tensor product of n of these individual states. And if you then take the inner product with the basis, you find this is the formula. And it's just a sum of these basis states with charges k1 to kn. All the coefficients are 1 up to the normalization factor. And the total charge has to be 0, namely, because you start from something without charge, you have to end up with something without charge. And we use this in our papers on quantum information. Zhengwei, Alex, and I. We thought this was a very nice state, and it provided a resource state which was maximally entangled with some measure of the entropy. But then we discovered, this is the normal formula for the state max, where this K1, K2, Kn charged state is just the descending state. Because these have the para-isotopy property, if you move one charge past another vertically, you have to choose an order, and this order of descending to the right is very natural. Okay, then we found out that there was another resource state for n-particle quantum information that had been invented by Greenberger, Horn, and Zeilinger, and was used in a standard way in quantum information. And it seemed to have many of the same properties. So we finally, this is the formula for GHC. GHC was Greenberger, Horn, and Zeilinger studied the d equals 2 case, but the formula for d equals 2 has a straightforward generalization for arbitrary d just by extending the sum and changing the normalization factor. And this is another type of Bell state where if you take the simplest case for d equals 2, it's the sum of the state 0, 0 plus 1, 1 divided by square root of 2, which is called the Bell state in quantum mechanics. And then we realized that these two states are just Fourier transforms, ordinary Fourier transforms of one another. And that calculation is very simple. It's just, again, one line once you realize that it's there.
This should be a picture.
Yeah. Right. But now, so we use this resource state to reformulate the quantum teleportation protocol of Bennett. That says if for a single qubit you have a state, Alice would like to transmit this state to Bob, and this state is just a sum of basis states. And what this protocol does is, since this channel here is a neutral channel, there's no charge on the lines, you can deform the channel by raising the in the middle to the two lines to go across the barrier between Alice and Bob, who are some distance from one another and want to communicate. And if you have isotopy invariance, then these two are the same. And the quantum information protocol says that you make some measurement in Alice's neighborhood, and this is just determining from the measurement which basis vector is involved. These are minus L1 or L2, and this information is transmitted classically to Bob, and Bob then performs a transformation based on knowing the numbers L1 and L2, which here is a product of two of the Pauli matrices. So this simple picture, because this part of the picture is the entangled resource state, this part of the picture is the measurement, encodes in a very simple way this protocol, but we could use these pictures, this type of picture, to find some other protocols, some new multi-body protocols, and eventually we got a much better understanding of this picture. So this understanding came from studying the so-called Kataev map in condensed matter physics, where instead of representing the single qubit by a charge k or minus k, you represent the qubit by a neutral pair. So you pair k with minus k for the state, that's just a model, and normalize it as you need to. And you would like to focus on the d-dimensional subspace where k ranges from 0 to d minus 1, but you're in a d-squared dimensional space, because if you took k and L, you'd have that many basis states. So you can find the algebra for x, y, and z on these one qubit states, and this is a solution to the problem. And this solution is very much like the representation of spin matrices by two Majoranas that was written down by Kataev, but works in the D case. And the problem is that the XYZ is not a constant, but a constant times this matrix, which is a unitary with eigenvalues q to the k. But this is in the big d-squared dimensional space, and since x, y, and z in this picture are each of them neutral, unlike the original picture where two of them were charged, they map the neutral space into the neutral space, and so it's natural to restrict attention to the subspace where gamma has eigenvalue 1, and then the algebra is correct. And that's worked for a single qubit. Now, actually, there are three natural bases, this basis that I showed you is the Z basis that is like the single qubit case. This one is an eigenbasis for Z, eigenbasis for X is this picture, and the eigenbasis for Y is this picture. So there are three ways of combining, of taking pairs, and they correspond to the three directions in space. And here the blue labels are just the four parafermions that enter the picture. So the multi-qubit problem is that this neutrality gave a very nice generalization, but and the beautiful thing about this is if you work with neutral things, you can get back to isotopy rather than para-isotopy. But the neutrality was a problem because if you braided in your transformation two strings from different qubits, these strings will have charge, and so it would destroy the neutrality. So the solution to this problem was what we called quons, and it took a little while to find it, but the solution is to regard the single qubit not as a picture in the plane, but rather a picture in three dimensions. So the qubit becomes a quon, and that's a hemispherical cap, so it's a solid cap, and these four lines coming out are coming out of the cap, out of the boundary of this hemisphere. So that's the one single excitation. And then if you have three of them, here's a tensor product of three of them, they're connected by some transformation, so it starts to look like topological quantum field theory. But it has this additional structure that these strings are connected to these points, which can carry charge. So you could think of it in this form as TQFT in strings. So with these different bases, we found it was natural to put the points not on a line, but in the square. So to move 1, 2, and 3, and 4 down below, and then this Z basis would have the connection above and below for the pair, while the X basis, for instance, would have the rotated picture because you're connecting 1 with 4 and 2 with 3. So this is just a rotation in the plane that reminds you of the Fourier transform. And we also have a natural reflection which doubles the system. So in our picture of reflection positivity, the reflection from the red world to the blue world is this doubling theta, which is an anti-unitary. And by rotation, if you can isotopy the picture, it rotates to the C-star positivity. That's the positivity of the inner product. And so it's an immediate connection between this reflection positivity, which is the pairing of the red and blue, and the C-star positivity, which is the pairing of the red and its adjoint. So if you go back to the quantum information and reinterpret it in terms of these pictures, this is a 3, so this picture is a little more complicated. The square, this is a cross-section of the three-dimensional picture where the square in which these endpoints of the strings are located are here 1, 2, 3. And the sides of the square actually are not the strings. They should be in a different color, but I didn't unfortunately draw it that way. But in this picture, if you take the state where this outside blue is just indicating some enclosing manifold, and then here we connect the top point up here to the bottom point here on left and right, and connect these other two corners of this square to two corners of this square, two corners of this square to two corners of this square. Then if you calculate it in the standard basis, what you find is that the only contribution to this state is one that arises from equal charges for the three quons, 1, 2, 3. And therefore, it just corresponds to the GHZ state. And in fact, all the coefficients are the same. Well, if you rotate the picture by 90 degrees and do the same calculation, the connections now have a different meaning because the picture has a different meaning. And what you find is you get two loops, and each loop is characterized by the fact that the sum of the charges in the three squares vanishes. So that's the max state. And so the relation in pictures between the GHZ and max in this notation is just given by a rotation. Now, if you put these two states on top of each other and connect them with a tunnel, this turns out to be the quantum C0 gate, which is also called the Feynman gate in quantum information. And here's the three-dimensional picture, just where the manifold is taken away, but to simplify things, just the lines are drawn. And so it connects two qubits to two qubits, and put the labels here so you can trace where the lines go. So this is the C0 gate is the central part. Controlled knot is a controlled transformation where you act on one qubit depending upon the value on the second qubit. And this right angle corresponds to Fourier transform. In fact, this picture of the teleportation of the state of Alice over to Bob corresponds to the classical, this is the Bennett protocol, and you can see in this picture the various components. So the resource state is given by this band, the measurements here and here. This Fourier transformation is the angle, and this C0 has this tunnel, and the recovery map is indicated here by the Pauli matrices. Well, Lusa Zhengwei drew this nice picture where she encapsulated the teleportation, quantum teleportation in the background with the classical communication over the telephone. And we're very happy that she labeled it 3D topology discovered underpinning quantum teleportation. So after getting involved with these things, Zhengwei went off in another direction with Feng Chu, and we think that these quons are not only good to study quantum information, but come up in other areas of mathematics, and here are a few areas of mathematics and physics that they seem to be related to, and I think Zhengwei will touch on many of these things in his talk. So I will leave it to him to fly over these different connections. What we think about of this language is that the language is something abstract used to simulate some particular problem, and might be a different type of problem in different areas. We call this the simulation clock, because as the clock hands move around, they point to different things and they connect different objects. So if you can prove theorems within the language, within the pictures, it could ensure different types of results in different types of things. So that's something where some of these connections are only really at the beginning. Particular functional analysis, how to do the functional analysis on pictures is a very interesting subject where not so much is known, although pictures have been used in analysis a lot, Feynman diagrams and estimates on Feynman diagrams and so forth. Well, we've written a little paper that's almost finished called a picture language program, where we have described a bunch of these things. And I'm a little early, but I think this might be a good place to end up with some other types of pictures. These are pictures from Cambridge. This is a picture where you can get some inspiration from punting on the cam. And this is a famous view, which is also very inspirational, maybe a little off-putting if you have an office that looks over this view. And here is a very good place to have inspiration, and it's been wonderful to be a guest here. So I think that's a good place to stop. Thank you.
Any questions or comments?
Paul?
One of the things about these special values that Vaughn found and you mentioned is that there's places that these values, there's Jones-Wenzel projectors in one context where you can set some linear combination of pictures to 0. Does that have any application within the quantum information type objects you're constructing?
Well, we've been using this picture in quantum information only with one particular value of delta.
Okay.
Delta equals square root of d.
Right, but this is now setting d to be, whatever, square root of 3 or, whatever. D equals 3, say, or d equals the golden mean. And then you get these additional special relations that might mean something. Okay, I guess the answer.
I don't know.
Any more questions? Or comments? If not, thank you again, Martin. So we'll restart.